Okay, so we want to take the lesson we learned from Wigner. He said to understand particles, look at the isometry group, the unitary irreducible representations of the isometry group of flat spacetime of Minkowski. So we want to do this for De Sitter. So we change the isometry group and we want to organize questions related to quantum field theory or holography on De Sitter with respect to the unitary irreducible representations of the De Sitter group. So I will call this isometry group as the De Sitter group. And we are focusing on fields in bulk De Sitter, but we are using these coordinates, conformal planar patch coordinates, because we have some motivation coming from cosmology, and this is the coordinate system we use in cosmology. So it doesn't cover the whole of De Sitter space-time, but it has access to the full late-time boundary. And by studying free fields in the bulk, looking at their late-time behavior, we want to identify some operators in the boundary and match that with unitary irreducible representations that have been well studied in mathematics literature. So we started doing this work with Konstantinos Skordis at SECO at Prague. And the main lesson we learned was, while the Klein-Gorder inner product is perfectly fine in the bulk, that's the way to normalize the mode functions in the bulk. For the things that appear at the boundary, you have to go and look at the inner products that the mathematicians tell you. So we focus on the group theoretical inner products at the boundary, and by checking that the operators, let's call these late time operators, the late time operators we identify from the bulk field, they can be normalized with respect to these group theoretical inner products. And we have done this work for spin 0, so we have done it for various masses. And I say here inner products because there's a lot of, well, not too many, but some number of category of representations, and each category comes equipped with its own well-defined inner product. So that's what you have to watch out for, and that's how you categorize. Yes. GFT. But the idea is now, so the first slide was spin 0, now we are doing spin 1, and hopefully in the future we will do spin 2 to get some clues for. Yes, that's the next slide, what we want. But, oops, sorry. So, yes. So in today's talk, the focus will be on a spin 1 field, and this will be a massless spin 1 field. And we hope to capture discrete series representations at the late time boundary from this, which we could not do with the scalars. And I will tell you why. So that's the main thing. That will be the main message to take out of the talk. So what I will discuss, first I will discuss the De Sitter geometry and the isometry group. Notice that this is one of the Lorentz groups. I will briefly review this categorization of the unitary irreducible representations to point out to you what are the discrete series. They are harder than the other representations, so I will emphasize this. And then the goal is to recognize some discrete series representations from the late time operators. And what will happen is the helicity labels will play a role. So the lesson we know, the wisdom we get from the group theory mathematicians is that among exceptional series type 2, so this is one of the categories, these are known to be reduced into discrete series plus and discrete series minus. So these are the irreducible unitary representations. And this is it. You can only find this in certain number of dimensions, and we take this as the way to find discrete series from the exceptional series type 2. But note that discrete series themselves have a categorization. There are two types, plus and minus. What we'll learn is that helicity labels track this, plus and minus. And actually, that's why we could not encounter these with the scalar field. I will give you, yeah. Mm-hmm.
There is much more.
There is much more, and I will give you references. So I will give you the reference I mainly follow and new references, old references. It's not like an exhausted list. It's just the ones I find convenient to work with. Yeah. And actually, every time we write our papers, we also review. At least to the extent we make use of it. Not like a full review, but you will see there are categories and there is some naming. So just take it as what there is a number of exceptional series. One of them is a bit more special. It breaks into discrete series.
Scalars, depending on how big the mouse is, series and principal series, and then make the massless.
Yes.
Is a kind of.
It is very subtle. We will discuss that, why it's a subtle, yes. Mm-hmm. So it's one of the exceptional series. Yeah, so it will be in one of the exceptional series that doesn't break into discrete.
Okay, just for audience, is each one of these some bulk particles?
Yes, yes, yes.
Each of them will.
I mean, we are doing it like take a bulk field in the center and find that what it maps to. And so far, we can always find some representation it maps to.
I guess the question, aren't they have possible if every bulk field
the other way, yeah, we didn't do the other way. Like, I don't have a proof like that, or I don't know. Yeah, yeah. I will also list those.
Hello.
So yes.
Yeah, sorry to interrupt. Audience, can you please use the mic to ask questions for the audience?
So this is just to flash out what you will see, okay, in details. So before we start, I think it's good to get thinking about the de Sitter geometry itself. And for this, let's go back to cosmology. So the standard fundamental assumptions of standard cosmology is homogeneity and isotropy. And these assumptions allow to have time-dependent backgrounds. And over the course of the history of the universe, the background itself keeps changing. The universe goes through different epochs. There are observations and theoretical reasoning behind all these epochs. And since Hubble's observations on Cepheid stars, so that's very late, or today's Planck observations, we know to trust in this time-dependent backgrounds. So there is something observable and physical about this. It's not just a question of, not just a mathematical or theoretical question. But among these cosmological epochs, there are two that in the ideal case can be studied in terms of the de Sitter geometry. One is the early inflationary epoch, the other is the current dark energy domination. We take some motivation from inflationary studies. That was the reason behind our choice of coordinates. So not the full global de Sitter, but the plane impact. But in a bigger context, de Sitter geometry is like a member of a bigger family of maximalist metric spacetimes with a cosmological constant, and it is the one with the positive cosmological constant. So actually, we want to, this is the bigger picture. So we want to be able to compare ADS, Minkowski, and de Sitter with each other and look at it as gathering new tools of how KFT works in different space-times, how holography works in different space-times, and we trust the representation theory, as the wall to lean our back on.
But representation theory and what global, this is you would have come same answer.
Yes, but actually, one of our collaborators, Vasilis, he always worked on global before joining us, and he says that the late time, the focus on the planar patch and late time makes everything much easier. I mean, he has more experience with the global side, so based on that, he is saying this. So yes, you can recognize these things from the global picture too.
But a matter of practice.
Exactly. Yeah, it's matter of practice. Yes, more or less, ma'am. It's a bit because we are coming from the cosmology background. That's the reason. And so as cosmologists, what do? We compute correlation functions, so not just 2-point functions, but for now, let's focus on 2-point functions in the early universe. And especially, we're interested in 2-point functions of scalar fields. And there is a way to like format this like a cookie shaper. So overall, there will be some amplitude of these correlation functions. And here, K, you've gone in from position space to momentum space via Fourier transformation. So there will be a piece that keeps track of scale dependence. And we can frame this as an exponent. And then the observations of the cosmic microwave background, they do go and make measurements and tell you values of this. This is called the spectral index. And what they measure is something very, very close to 1. So Planck gives you this number. It's not exactly 1. That's what makes inflation itself different from exact de Sitter. But let's stick with the case that it's almost 1. So let's focus from that perspective. What that means is, because of this parametrization here, it means there is no K dependence. There is no scale dependence. So you get a scale invariant power spectrum. And this is also what you get if you study the correlation functions of a free massless scalar on the system. So this is the connection, what makes the quantum field theory of interest for inflationary studies. No, it's for all wavelengths. It's for all K. Why? Whatever you have, you can look at it as some amplitude, and there will be some K dependence that comes with an exponent. It's just like giving a name to the exponent. Mm-hmm. So actually, yeah. Supervised. It's like a so then, so in the early 20,000s, people started coming up with this concept of how to study de Sitter in holography. And this is not the only paper. It came together with Witten's proposal that focuses on establishing a Hilbert space, Strominger's proposal that focuses on establishing some RG flow from the early de Sitter phase to the late de Sitter phase. But this one did two things. It summarized the cosmological correlations really nicely. The problem of the difficult part with the inflationary correlators is handling the gauge fixing well. These scalar modes can appear in the metric or as a perturbation to a scalar field. So he clarified those gauge transformations. And then he said to look at the 3-point functions as well. So that's where you will see the deviations from the sitter. And then he proposed that how might you do this in the setting of holography? But his proposal, Maldaceno's proposal was to motivate it from ADS-CFT. So just like the partition function there, he imagined some version of it for the sitter. Then some years later on, so this people said, okay, so now let's compare this with the observations. It has been so easy to detect scalars. Yes, tensors are expected to be harder to detect, but still, why are we not detecting that? And they said, maybe actually, if we do manage to study this in the context of holography, we are just at some fixed point, which makes the tensors so difficult to see. And these fixed points can be described in terms of slow roll parameters. These are some inflationary parameters.
Sorry,
Yes. Yeah, there is, yeah. Yeah, true.
Sorry.
No, actually, thank you for saying that. Yes. I meant to say, no, I meant to say, I forgot to say that I just took some papers that came my way first, like that. But yes, there is the many literature in between. And then, so more closer. So there's this one paper. This is more like the Witten proposal. They are actually trying to establish a Hilbert space, and they study higher spin theory on the sitter. So this is like the cousin to higher spin on ADS, giving an ON model. So there was earlier work on that, in fact, by one of the authors themselves, Dionysos and Ninos, where they thought it would be SPM model, but this paper corrects it. It's actually, they propose something they call Q model. It has O2N symmetry. So they start identifying these late time operators from the higher spin theory, but they cannot make full sense of it. So this is not the end of the story, but this is one step towards coming up with that.
The wave function will be the partition function of some incredibly non-unitary.
Yeah, this is more like that. This is really trying to find the operators, the states in the Hilbert space. Yeah. They do wave function calculations, yes.
Sorry, just to understand that we on a future. So are they looking at the Hilbert space of the field? Yeah, the Hilbert space of bulk is partition, wave function of the bulk is partition function.
In the late time limit. So from the bulk, you study the bulk, then you take the late time limits, and whatever you read off at the late time limit, that's supposed to be.
So we don't get a Hilbert space from some the Hilbert space we get another level.
Not from the bulk. So yes. So they're saying don't try to do some analytical continuation of the ADS boundary Hilbert space. So just studying from the bulk and taking the late time limit, understand the operators you have there, what kind of a CFD that would be, what kind of a Hilbert space that would give rise to.
Bulk. They just analyze bulk
But in the late time limit.
in the late time. The boundary field can replace no role. Understand that?
The hope is that this gives clues towards what the boundary is.
So the Hilbert space, yeah, fine.
Yes,
From the bulk,
yes,
from bulk.
yes. No, so in the late time limit, it is like for the late time operators, it is this group theoretical inner product. Well, from the operators, you do you act with the operators on the vacuum and define states, and you need to use those states in the inner product. So this will be different. So wait. That was the message in the beginning. But they're saying that that is not the correct one. Sorry, I keep forgetting. So that was an earlier proposal for SPN. So that was just from analytical continuation of the ADS-OM holography. So they're saying if we do this from bulk to boundary, we actually discover something matrix model. It doesn't say it in the abstract, but they have something with an O2N symmetry. No, this is, yeah, so this is correction to that. You don't need, no, the group theorists have worked out the inner products. Yes, so. Yeah, it does, like that state operator map is not exactly like ADS. Like you don't have this radial quantization things. So you can identify operators at the boundary, you can define states from them, and you can check whether you can normalize these states with the inner products listed in mathematics literature. That's what we are doing. That's what the not with box states, no. Like you will see.
Okay, it's good.
We'll see. So in this paper, so they give a correction to Maldacina's proposal between the such wave function and the partition function. So they focus on heavy scalars in the principal series, which you were working on. And they say like there are some terms you can neglect for the light scalars, but you cannot for the heavy scalars. And the effect of these terms, it is what gives the correction to that, what the partition function might be. And they comment on this in terms of double trace deformations.
The last time. This other quite correct. It's actually good.
Okay. Well, thank you for saying. So those are some motivations, and these later references start pointing out towards the representations. So that's sort of what we're doing as well. So back to the correlation functions, and remember that we wanted to think of the sitter as one of the maximum symmetric space times. So these are the other ones we want to compare it with. And maybe you will agree or disagree with this list, but we know quantum field theory on Minkowski well enough. It's like a standard textbook level. We know holography on ADS very, very well. That's what started it all. But, you know, if you want to do both these things for everything, you know, there are some question marks, and most question marks are on the sitter side. And the lesson is, since these are open questions, maybe the answers are very unintuitive. You know, if intuition for QFD is coming from Minkowski, if intuition for holography is coming from holography. So it's just, you know, be okay with that.
Hi. What is the problem statement for a D-sitter QFT?
Or what is the, which method?
What is the problem statement for a D-sitter QFT?
Like interactions, understanding interactions, locality. Those are what
Okay.
is, how to write down local.
IR diagram.
Yeah, exactly. IR divergence. Yeah. I will not talk about IR divergence. Mhm.
Just has to do with the time.
I thought what's going to happen is that no particle needs it. Because it's time dependent. Eventually, every particle goes to do what's about. That will work. I think there's one computation that I thought right for maximum things, which computes the Dubai function and finds that spectral representation, which is delta function, something like that. Representation, very level, gets spread out, which is what happens at least in that space. There's no delta function, which seems to suggest maybe one thing, so just one look at that. You see, in that space, if you've got nothing to decay to, you can't. And so the life is part of the always thing. Because it's time dependent. Everything is fine. There's nothing stopping the particle from. That's what I thought. But so basically, no particle completely stable, just like the phone. So that's part of the story, right? I would love to hear it.
You must not tell you just because this it's extremely just which I understand it, and it's true for the reason.
Okay, so let's go back. So what we are trying to do with this identifying representations at the late time boundary is to give some list of operators at the boundary and their correlation functions. And actually, we are just hoping that someone who knows CFDs well can look at this map, this list, and tell us, oh, yes, I know this CFD that has these. So earlier on, the studying scalars, these were the results we got. So for each scalar field with a given mass, we identified two operators. And these two have non-trivial commutations with each other. They are different than each other. The heavy ones we could categorize in the principal series because they can be normalized with respect to the principal series in your product. The light ones in the complementary series. The massless scalar, now how you treat it depends on the number of dimensions for reasons that will become clear more and more. But we could put one of the two lifetime operators into the exceptional series 1 category because that was the inner product that went with it to normalize it. But the other one was in the complementary series. So this massless scalar case is still puzzling. But for all of these, if you wrote down the 2-point functions, so these are the bulk field and its conjugate momenta computed with the wave function method or with the canonical quantization. Take the late time limit. You can also compute the 2-point functions of these operators and you get some matching like this. So how these late time operators contribute to 2-point functions are they have their self correlations and then some mixture of the two. And so in the complementary series, so the one of these will.
So in the bulk, I could expand in terms of possible. And then get some coordination functions for the subsystem. Now, is your state some linear combination of fields in the
Yes, yes. But there's also taking the late time limit
sure.
on top of that. So actually, that's what we will work out for the vector field in the top. So it's delta 0 and delta equals 3.
Yeah.
Yes, yes, 0 mass.
One of them is I think that's the one which is.
Yeah. So this nu is not mass itself. It's something more.
It's mass minus.
Yes, mass square minus square root. Yes. Yes, what 0 is mass. Yes. No, M0. You see the. Yeah. If you think it like that, yes. Yes. We will get there. So this is just to flash you out how scalar examples fall under some of the categories. I'm just warming you into the naming of the categories. Yeah, there is some inner product between them. The massless ones. Mhm. Yeah. Mhm. Actually, wait a little bit, and then we will come back to this. But it is confusing why they are like that different. Okay, so first, let's think about the symmetries. Okay, so now we are starting the group theory. We're good there. The principal series ones will. Yeah.
That's the my so some choice of basis. This is not good. Yeah, good theorem. Yeah.
So let's compare the sitter with something we know well, the QFT version, the QFT textbook example with Minkowski. So these are the symmetries that the two spacetimes possess, the isometries. Now let's focus on what's different on these two lists. For Minkowski, while you have boosts and time translations, for the sitter, you have dilatations and special conformal transformations. So anything you organize your thoughts based on stuff to do with transformations of time, like time translations, you have to rethink now and put the emphasis on dilatations and special conformal transformations. This is also what makes a matrix program difficult. On this, we don't have time translation. The unitary reducible representations of the de Sitter group are very well known to mathematicians, and they are like, pretty much established by works of Harishandra. And then there are all these reviews. They take different routes. You can construct these representations from the algebra. So this is an old paper where they're comparing the two-dimensional de Sitter group. So that will be SO2, 1 with SO3. So a group we know very well. And this is a more recent one where they're focusing on the principal series representations, also on 2D, I believe. We will mainly follow this review by Dobrev. So they have written a book on Euclidean CFT, but that has all this de Sitter quantum field theory in it. So either you can read it as a Euclidean CFT book or a de Sitter QFT book. And they focus on constructing the representations from group elements, so not from the algebra, but they are only dealing with bosons from spin 0 to so on. Then there's another way to do analytical continuation from SOD plus 2, so from the sphere. And this works a little bit differently if you're in two space-time dimensions, so one space dimensions, or above. So Higuchi has done this for bosons, like he writes all the symmetric traceless tensor spherical harmonics, and then maps them to those two representations. And Vasilis, who's also one of our collaborators, now he's a postdoc, but he used to be Higuchi's PhD student. He extended this program for fermions. And these days they are doing things like, they also bring in supergravity, supersymmetric theories on the sitter and try to identify these representations. So they try to identify graviton and gravitino, and they also see them in the discrete series. So that's the different than spin 0 and 1 case, actually. Yes, but it's a very careful method. But So, okay, maybe you will be happier with our way. We will not do that. So we will construct them from the transformation. So basically these people have done it and reviewed it. So we go and look at them as the resource. But we agree with these other things, agree. So first, let's talk about labeling the representations. So for this, we look at the quadratic Casimir, and the quadratic Casimir labels involve the number of spatial dimensions. Okay, this is fixed, you can fix this from the start, but what is there for your field of interest is spin, and there is this piece that knows about the mass of the field called the scaling weight. So remember we had dilatations in the list. So fields or operators transform this way under dilatations, and from here you can associate a scaling dimension to them. For the de Sitter group, the format of the scaling dimension is fixed. There is a piece that knows about just the number of spatial dimensions, and then this second piece, so this also has a number of spatial dimensions information in it, but this involves mass and for non-zero spin information in it. So all the properties of the fields.
Just according so format to the representation by SO2, the eigenvalue, I mean the representation of SO3 times SO2 of the primary element.
Okay, so SOD is this L. Instead of SO2, now we have SO1, 1.
So here we read SO, this what SO3, 1.
So label L is with SOD rotation.
And in the group values that is SOD, 1.
No, it's SOD plus 1, 1.
So that's what I want. Why SOD plus 1?
So okay, we will get there. You're asking about this.
Yes, there's a larger compact.
Yes, so we will discuss this. So there are two sets of invariant subgroups. This alone is one of them. This is the one that gives rise to discrete series, but there's another one that gives rise to principal and complementary.
But let me just ask once more this because it's structured and SOT, 2, which is the same dimension in this group. You label representations by the representation label of maximum compact, which in that case was SOD times SO2. And that label primary state, and then you build non-compact part for instance. So if I was going to make that analogy, I would have thought, okay, I'll just look at the maximum compact subgroup. That would be SOD plus 1. And I would label represent the states by that, and then there would be something I would have vaguely thought. And you're telling me that's
that is not the whole story. There is that, but there is more. Not two maxima, but two invariant subgroups. Yeah, so Cartan generators are rotation and dilatation. And then just this next list actually, this is what you're asking. So now looking at the invariant subgroups, so this was just all of translations, including time translations for Minkowski. Here you have two kinds. So this is the one you are looking for, the maximally compact subgroup, but there's another one made up of rotations, dilatations, and special conformal transformations. And the generators, so some of the generators in here are linear combinations that involve special conformal transformations and translations. So like some of these generators also make an appearance in a complicated way in here. So here also you have that.
SOD, the labeling of representation, labels by both the maximum and compact. Here, it won't be the representation that just labeled by.
Not just that, yes. But these labels, so I'm introducing them from the dilatations, but they will get a bit more complicated, but they will also capture this maximal compact subgroup labels. Okay. So to compare, when you focus on translations, which involve time translations, mass itself is one of the labels. Spin is always there. Mass itself is one of the labels. But in this case, it's not mass as it is, but it is this piece that goes into the scaling dimension. So maybe let's. For you, keep remembering.
Suppose B was, I will be approximately B was 4.
Yes.
Okay, suppose B was 4. In this case, we have 6. Yeah, so that's SO5 for.
No, so D equals which D? D equals 3 like dS4.
Yes, right. Okay. So in this case, how many labels you have? How many real numbers you have specified here?
2 labels, but they don't need to be real. That's the tricky part.
So SO4 would also add 2 labels, but that's not complex. Okay.
So the color coding goes through. So spin is coming from SO little d, and the other one is coming from dilatation. So no translation. Okay, so now these are the categories of representations. So you see this label C, it's not restricted. So the full scaling dimension here is not restricted to be real because you don't have time translations. And unitarity means being able to find well-defined inner products. And actually, it works the easiest in the case where the scaling dimension is complex, with this C, the scaling weight, being purely imaginary. And that.
Delta is the SO1 comma.
Yes. Yes. Good. So delta is the SO1, 1 weight, but yes, C is there.
Yeah, that's the real scaling.
Yes. So, so to compare with what you have as massive particles, so on Minkowski, you look at the little groups, the group that preserves some like momenta, which is the way you categorize these. Here you are categorizing them based on the ranges of what C can take on. So for massive particles, you just have the rotation subgroup and this many finite many states. So here you see you have an infinite number of values sigma can take. For massless particles, you had 2 helicities. So in this case, massless particles belong here together with tachyonic and partially massless particles. So sigma is, so now C can take on many, many values. We just have to parameterize it some way.
Oh, C is it.
Yeah. Yes, for principal series. Now, yeah, and then these are the question mark representations you were saying, right? The ones that we don't really know. But in this case, we seem to find so we don't find an example maybe for all exceptional series, or I haven't looked at it. That's why I say it like that. But in this case, so far we have been able to find examples for many of the categories. So now the cut is between this scaling dimension being real or complex. So when it is real, the inner product becomes more subtle. This means how to identify the adjoint of a cat state. And it involves extra maps. So this is your question, actually. It involves extra maps. And you have to be careful for in what range of C, these maps are well defined. What happens is, so for unitarity, you want an inner product that is preserved under all the de Sitter transformations. But the way dilatations work so the way the mathematicians write is in terms of function spaces. They tell how the functions transform under the two transformations. There's a way to write this in terms of group elements. There's a way to map this to position space. So you know how the functions of your function space transform. The inner product of these function spaces should remain invariant under the two transformations. Dilatations become problematic in these transformations. So, okay, this I will not go into details in the interest of time, but later on, if anyone asks, what happens is altogether they bring in a factor like this. Okay, so some difference of this. So this is a dilatation element. If you write this in position space, if you do a Fourier transformation, this appears as the exponent of momenta contributions. So you see, if C is purely imaginary, this automatically vanishes. That's why the principal series, the heavy fields, are the safest ones. Everything goes through. In the other cases, in the cases of real C, if you can find an operator that will map your original operator to something that has the same spin but the opposite scaling weight, so that this factor drops out, then you're good. So you go and look for such operators, but this needs to be an invertible and normalizable operator. And in position space, these come out to be the 2-point functions of a CFT. So they are not very strange things either. The normalizability property, the invertibility property, these are important. So this is what categorizes the real scaling dimension case further. So you need to use different operators. These are called intertwining operators. And what they do is they map something of dimension D to, D minus delta. So it works like the shadow transformation. It is a shadow transformation.
Like 2-point function is non-zero between the representations.
Yes. And this defines the complex conjugation. It's just, it's, if you like, this is what is defining your complex conjugation.
Is there a special state in SOP comma, D comma, there was a special state, the primary state, which was a state of lowest state. And that we use that. In these representations, is there a particular special state which you call a primary state, which you might want to call a primary state? How is it?
So my understanding is each S delta would be a primary. So it's not like lowest, but
That's a, those
that
represent living represent.
Yes. So
I fixed my state and my delta. Now, in the usual superconformal, once I give you a representation, there's a particular state, the state of lowest dimension. Everything else is built on top of that by a okay, and that primary is like a very special state. If there's an analog of that within a given.
I am not sure how to identify that. Also, maybe that goes through with discrete series, but not with the other series, because you can identify the translation and special conformal transformation generators to raise and lower the value of delta by integers.
And is there a lowest?
From there, you can find the lowest delta, but we checked with one example. We were looking for it to go all the way up. At first, we thought we can get that, but then we found the mistake, and you don't go all the way up. So it connects some of the representation. And among the discrete series ones.
I think about delta is d by 2 plus c. Now delta is just one of the data, one of the generators. And we'll take different values in different states in there. But C wants at least a label that represents it. Like, I'm getting confused.
No, delta and C are related. You
C
can,
is labeled represent. Right?
yes.
But different states in the in the same representation will have different values of them. So how can that? Isn't that right?
But for a given C, you have a specific delta, or am I confused?
Are you saying that all states represent this representation have the same value? Meaning, let's say in an SU2 representation, different states have different values. You don't label the representation like this. You can if you have a special state, like the highest state. Then the representation is labeled by them.
Yeah, so that's highest weight. Yeah, because
This one is D plus 2, right? Okay, but then it's not delta, it's not the value of delta. If a delta was a particular SO1 was the SO1 delta. That will take some value on various states. You get different values on different states.
Yeah, you can.
Which state for whose delta?
Yes, but that makes it, yeah, so yes, but then it's only for the discrete series that you can have integer values of delta. So you can act with raising and lowering operators, but if you do that on a principal series, you will not end up with other unitary representations, because they need to have this imaginary piece, and then it doesn't fit with the format. Yeah, it's +1. Yes, it's +1. But if you want to keep going to other unitary irreducible representations, so you see, if you add 1 to 3, 4, okay, that's still in here. But if you add 1 to 3 over 2 plus I times 3, it's not again 3 over 2 plus something. Like, it's some complex number that doesn't have the real part as 3 over 2 anymore. So it's not unitary anymore. So you can raise discrete series into other unitary irreducible representations, which will also be discrete series. You have some room in the complementary series too. You can raise them because these two have real and the exception series. So these are the ones with the real scaling dimensions, but you cannot do that with the principal series.
Is it right that different states, same representation, carry different kinds of data? I think if you replace the scale, the final value of the scaling of the economics. And I thought it wasn't that.
Yeah.
For the version. This is what I'm trying to understand. What is this?
No.
There's always a lower state. For sure.
But
not
here.
Delta is d by plus C. On the right hand side, C seems to label represent. On the left hand side, delta takes different values at different states in the same level. So what does that equation mean?
For a given C, you have a given delta.
This is what I'm not understanding. That two different states in the same representation, different values. No.
But you can have same Casimir values for different representations. No. SOD place.
Somehow. One changes it. So roughly it is the spin of the particle.
Yeah.
As in space spin and it's like the roughly.
Yeah.
Okay, so that is clear. So I feel that the real really going to the class. So then that's fine. But then it's not
Yeah.
referring to SO1, comma 1. The item value of a particular SO1.
Okay, this part you can rewrite as so delta minus D with an overall plus or minus.
Delta by plus correct. Then it's
And I
really
keep that. Yes,
But
yes.
Also, had the delta was the SO1, comma 1
Mhm.
generate. So that acting on which state? Doesn't delta change between states? Doesn't the eigenvalue of SO1, comma 1 change between states and state level?
Okay, maybe I don't.
JZ changes the suit. But not the particular value of the same.
So okay, D is not changing. C or T are changing delta, the value of delta. C, so special conformal transformation and translations can
can
change delta.
So, but they are part of the part of the group.
Mhm.
So by acting on with that, you generate different values. So
Yes, yes.
So then, how if this equation delta divided plus C, how is that related to delta being the value of the SO of the generator? That must be a particular state. So then there's some distinguished state. Then just for the time.
Okay, I think I tried to work out what you're saying, and it is a bit confusing.
Okay.
And I think it works, okay, the way you want it. I think it works for discrete series, but not for principal series.
Okay.
Yeah, I think, yeah. So if you go back here, you can think of things as highest weights of this in the analytical continuation to the sphere. But that highest weight categorization here works well for discrete series.
All the way. Actually, since it becomes complex, the value of delta becomes complex, but means even for it to be higher or lower.
Yeah, but you don't have that. But yes, that's exactly that. So there you don't have it.
Delta, whatever is so one, right? What does that mean?
So C can take on imaginary values, and it takes on imaginary values.
C is some fixed, for given representation, C is some fixed imaginary. But different states have different values. This is so one more.
But you can really identify some operators and work out how they transform under dilatations and really read off these deltas and hence C's. Does that help?
Yeah. Yeah. That's good. Yes, but then I think it's just a matter of labeling the thing. I identify that maybe the action of a particular generator on some state, and if so on which state. For labeling, I have no issues. It's a relation. Okay. For the real part. Okay, but is that a what's the specific one? Hold that. I also
So
it's difference. O of K. Then say for a scalar
that in the two lambda to get lambda.
Yeah, exactly. From there you can read.
Then you do for the lambda. Right, so for so now, the thing I don't know is the map between previous and states, but if there is such a thing,
Yeah, this is what I meant by you can work out how the rotation acts.
So maybe in the operator language.
Yeah, yeah. I will write something down, but I'm not sure if you will be happy enough to call it a map. But okay, so for these for the unitarity for these well-defined inner products, we need some operators, intertwining operators, invertible and normalizable. In the cases of real scaling dimension, which also have real C, but then how well-defined these operators goes with certain regions of C, so you have different intertwining operators in each of these categories. So the intertwining, the being able to define these intertwining operators as maps between functional spaces is what's categorizing, giving you the categories. So the normalizability I said is important. It involves some gamma functions and they can diverge at certain values of C. This is why, so this happens for the discrete series. This is why you need to use different intertwining operators for discrete series than you could have used for complementary series. But actually, remember, we will access discrete series from exceptional series. So they are actually getting the inner product from the exceptional series. Yes. So it's different in the exceptional series and complementary. And one of the exceptional series, because it breaks down to discrete, then so discrete gets its inner product from that particular. Yes. Okay, so now to
Hi, sorry, what is the category for exceptional series? What is the C for exceptional series?
so it will be certain. There are types. I will write them down.
Okay.
It is a little bit involved. I will write them down. It's like H over D, H being the Hubble parameter. So now this is some properties taken out of math literature. And so the results, the main results mathematicians came up with is that these kind of representations only exist for a certain number of dimensions, or even total number of dimensions. And if you're interested in symmetric traceless tensor representations, the dimensionality gets reduced even further. You can only access them, have them in 2 or 4 space-time dimensions. And what happens between this, under the transformation with this intertwining, the shadow transformation, in the complementary series case, the representation and its shadow are equivalent, but in a discrete series case, they are not. And this is the plus and minus categorization.
So the one with the one with imaginary stuff is called what?
Principle.
The one that is not imaginary but otherwise not exceptional is called
Complementary.
And discrete is special.
Yeah, discrete arises from the exceptional.
But it's something very particular.
Particular, yes. If you want symmetric traceless tensors, so if you want something more exotic, you can explore the other even number of dimensions. But if you want the simplest case, you're even reduced further to B2 and 4.
The other, this is you get 2+1 is even. It's different. But not associated with the boundary, which is something.
Yes, yes. Okay, so this is my encounter with discrete series so far. So we did manage to identify, so 2 dimensions is a bit special. We did manage to identify massless scalars in this category. So here they have another label. This is the SO2 label. This little n is the SO2 label. So that's the maximally compact subgroup label. And this was done in global de Sitter. So when you work in global de Sitter, it becomes easier to see the maximally compact subgroup label. But what happens is you have to be careful with the zero mode. You have to remove it because this massless scalar has some shift symmetry. And when you do that, that breaks the Tinkoff values of n, like on a line from plus infinity to minus infinity. It breaks it at n equals 0. It corresponds there. So the positive values of n are one tower that goes all the way up. The negative values are another tower that goes all the way down. And here you do see a particular highest and a particular lowest weight state. So how this works so this is your what you wanted to do. Mm-hmm. Two, yes. That little n is the SO2 label.
Yes. And then you remove the massless.
The n equals 0 mode.
And then you.
This is all for the massless field, though. So
and then you just have one representation from any point to
1 to above, yes.
Yeah.
Yes, so this is the one, but this only happens for discrete series. You see, not for principal series. And it becomes more clear in global de Sitter. So we are, when we are working in planar paths, we try to identify that, but it is difficult. But maybe this makes you happy. No. Yes, because of, so this is in the family of tachyonic scalars, and in the old papers, they already call them discrete. They already call the tachyonic scalars discrete. But actually, they are in a different exceptional series category that only the scalars exist, which is like coming up. So they are exceptional series, but not the one that gives rise to the discrete thing. That's why almost. So yes, massless, but massless is one of the family of tachyonic scalars. But so tachyonic scalars on de Sitter can also be identified with unitary irreducible representations. And if you look at 2-point functions, so this is also 2D. Meet, yes. But exceptional happens there, and one of the exceptions is discrete. Mm-hmm. And the 2-point functions in discrete series show different behavior than principal series. So you have these logarithmic terms and some extra pieces.
The daytime behavior starts under modes.
Yes.
So that's what makes it.
Yeah. Yes, but it's also integer for exception. And also integer for bosons, half integer for fermions. Mm-hmm. Yeah, so 2 lines. Okay, so 2 lines meet in the C plane, not the delta plane. So yeah, so you have the, so they all have the d bar 2 parts. Remember this, this one. So if you think of the imaginary, so this is for C. Okay. If you think of the imaginary axis, all of this is principal. Yeah, so this is at d over 2, and then you're gonna add another d over 2. So from C to delta, you have to add another d over 2. Okay, I will show you some pictures later on after the talk, okay? But like there is a, yes, I will show you. Okay, so now the exceptional series, we need them to better understand, and one of them will break into discrete plus and discrete minus. So, okay, this is taken from the Dobrev review. So remember, we said to label the representations by spin and the scaling weight. Now the exceptional series fall under these 4 different categories. So everything in the second entry of the parenthesis is the scaling weight. Everything in the first entry of the parenthesis is spin. So in the first 2 lines, this SOD label immediately is spin, but in the second lines, you have to think a little bit carefully. So there's also this sigma label. And they have some restrictions. Sigma is 1 higher than now. And then, so chi is for the representation, C is for the function space that representation can act on. And okay, they have gone and identified the invariant subspace. Just keep track of these plus minus signs and prime signs. That's one.
State function.
Yeah. Yes. 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 Exactly. Yes.
Kind of this particular right? And the functions are just right? So
yeah. 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 Yes. Yes. Yes.
Yeah. What states per se.
Yeah. Yeah. That's why operators. Yes. Okay, so now these 4 categories of exceptional series arise in math literature, but in physics literature, the focus is on these 2, and they just call them exceptional series 1 and 2. So it's just a bit different naming, but it goes with specific values. You see, L here is 0 now for this exceptional series 1 case. And it can take on these values up to sigma. If you are convenient with Young tableaus, in this context, L stands for the depth. And this is this group of people, they have also studied what we are studying, but they have done it on global coordinates. So the SO4 content is more clear in their work. So it's this last line, both for the mathematicians and for the physicists, that gives rise to discrete series. Where to look for discrete series? Some particular values of spin and scaling dimensions. So you see these now, we have these extra parameter sigma that has to take on, can take on these values. D plus 2 plus this.
That's
Yes.
always been a debate.
I think so, yes. But I will show you the picture.
So basically that label price. Choose your spin, go to where you are at the end. Is that right? Fine. Choose my spin is one place where these will be. And that's where your exception is. And then the one kind of spin you're type on the other end.
Yeah, I think so. Yeah. Yes.
That's tangent space. What's the spin of your part? Where the space in you're in a T plus one dimension space, so spatial tangent spaces. SOD. So spins of particles are labeled SOD. What kind of particle are you doing? What spin? And that at some particular mass. That's what I do.
But here actually, yeah, so here in these last two lines, L and sigma switch roles. This time this sigma is also important. So it's L plus sigma that captures spin. So if you are after S equals 1, either L or sigma can be 1. So then it's like for S equals 1, sigma starts to capture spin. It's a bit confusing in the last two lines.
I give this physical space, tangent space. My particle, I put it in. I fix that. That's not discrete. Instead of O, it would be labeled by G. SOP. And then I accept that maybe something is. And then I change the mass of it. Given that there's some particular mass for these spaces,
there's some particular mass.
Yeah. And now that I know what my labeling is because I just go to tangent space and I look at the spin. Unless it's.
But here, this piece also governs the spin information. You see, this label L appears both here and here. So you have to fit the spin value with here and the scaling weight value with here.
That's all.
The sigma is not, it's this plus D plus 2 is the SO1, 1. Yes, sigma is complicated. I don't have a, like that. Okay, no, the things changed now. This is a different sigma. So, no, keep track of this. Yes, L plus sigma is the tangent space. That's why L and sigma. So that, yeah, if you so they can identify it as the depth of the Young tableau in these. Law of dilatation.
Eigenvalue of boost at some stage. Okay, you're saying operator. In the figure 4, all I need to tell you is what my tangent space is and mass. Then there's no further.
So actually not mass, but this. See, that's mass, but scale this information of scaling dimension. You want to call it?
When I'm saying, I give you the wave equation. Wave equation has a parameter which change what you call it. And of course, it has some tangent space too. Now, I would imagine that is labeling representative.
That is labeling representative.
So now you can move what I'm calling mass. We know that something special happens as we go from one range of masses to another.
Yeah.
That is at late times it goes from decaying and growing to oscillating. Now there's one particular value which will be the transition. There's something funny can happen. And I was imagining that what's happening is always choose your tangent space, move your mass to this particular value and then transfer. That right?
I think so. Yeah. Yeah.
And then
Yes. Yes. The second, yes, which is the second entry. dilatation.
Sounds good. But I could relabel by house.
Yeah.
Sounds good. And then, but then one and two, I was like, between one and are both at different tangent space spin values, or at the same tangent space spin value, for example, two relative. That's what I'm
What are you calling like
saying.
one and
Exception
two?
series type one and exception series type.
Yeah, see, one of them just has L as its spin value, the other one has L plus sigma.
Okay.
Yeah.
So different tangent space.
Yeah.
spins.
Yes.
So is it
That's-
sort of, I see. But you know, suppose I choose spin equals something fixed. Let's say I choose spin equal.
Mm-hmm. This thing should equal 1.
That thing is equal. So as spin equals 1, do I both have exceptional type 2 and exceptional type 1?
No, you have exceptional. You have exceptional type 2. I don't.
Plus.
Mhm. This and this. Yes, you have this and this. Yes, you have. Yes, you have this and. Mhm. Yeah. You have that and that. Uh-huh. The first entry is also different.
Yeah. Is it a different Wien equation? Or is it that the same Wien equation actually breaks up into two elements?
Yes, this is it.
This-
That's why I keep saying alpha and beta, not just one. There is a different delta.
Yeah. So you're saying
Yes, not for mass, but for delta. So deltas are different. So a given mass gives rise to two different
so the same
deltas.
equation breaks up into two
Yes, that's why I had an alpha and a beta. Yes,
elements. So boundary hinge.
exactly. Yes,
Boundary
Yes.
hinge that you get.
yes.
It's like what's
Yes. Mhm.
You exchange between.
Yeah.
But we cannot mix between
Yes.
the.
Yeah.
isn't it?
So that's why I flashed out all those things with alpha and beta. They are not commuting with each other. Yeah. So
Right, so
that's. Yeah, so that's confusing. So the first entry captures spin. So for example, if you're looking here, L itself captures spin. But if you're looking here, L plus sigma captures spin. And they also appear in the second entry. So for a given C, from the second entry, you can determine what value of L and sigma needs to be such that it will also give the correct spin. So these are all the exceptional series categories. And the discrete ones, we will look for them in here. So they get these extra labels, L and sigma, that work into our main labels, S and C, in this particular way. A different way for each category. So what happens is you can put M equals 0, S equals 0 here only. Like this starts at non-zero S. So that's why you could not have the exceptional series type 2 from the scalars, from the massless scalars. So now let's really write out the problem. So this is our choice of coordinates on the planar patch of the sitter. And this is our action. So just a free vector 1 field. Now, we leave it for future to go into the details of different gauge fixing tubes. We just fully fix the gauge from the start. And we do the mode decomposition. So maybe let's go a bit quick in the interest of time. This should be standard. So we write down the classical equations of motion for the modes. And we pick the solution that obeys the Bunch-Davies initial conditions that dies in a certain way at early times. So you get Hankel functions depending on your IF prescription. It's type 1 or 2. So this is what we get. So here, this overall coefficient C, this you can determine from Klein-Gordon normalization of these modes. Okay? So that's where Klein-Gordon normalization goes through. Now, in the mode functions, since these are tracking a vector field, we also have polarization tensors. So this is the difference from the scalar field. And these are the defining properties of polarization tensors. They are perpendicular to the direction of propagation. And then we do canonical quantization. So in the beginning, we had some coefficients that were just numbers. Now we promote them to be annihilation and creation operators. And this is what we call a state, one that it gets created by the creation operation operator that also has this these labels. So this is the dictionary, the holographic dictionary we use. So in the late time limit, you can read off the scaling dimensions from the exponent of the time dependence, and it reads something like this. So this new here now is the C on the board. So it involves spin information and mass information. So the range I set between heavy and light, that was for this scalar case, just this sum M over HD. So you can read off the operators from the remaining part. But then you can go and, so the operators you read off, you can go and look how they transform under dilatations and confirm that indeed these are the dimensions they have. So we do that. This was our solution for the mode functions field. We are working momentum space. So we actually read off the momentum space versions. We can take a Fourier transform to positive space. Where we take the late time limits, we just have to be careful with the limits of the Hankel functions. And we get this. So the late time operators, now these are our late time operators. They are made up of polarization tensors, annihilation and creation operators, and they come with some K dependence. So this K dependence tracks C, actually, the scaling. So looking at what happens to them under dilatations, we can read off the dimensions. So we call the one with the lower dimension alpha, the other with the higher dimension beta. They look like they're shadow transforms of each other, but if you do that, the transformation does change these pieces accordingly, but it doesn't touch this polarization, annihilation, creation part. So they're not shadow transformations of each other. They have their own shadow transformations. Though that's the tilde versions. Okay. And reading just the K dependence. It changes the K dependence, not this, all these other ones. So knowing the scaling dimension and this important piece from the scaling dimension and spin, these are the labels. So now we have to see under which of those 4 lines these labels fit and how. So it turns out that this prime plus was the exceptional series type 2 category. So beta fits here. The other one is in prime minus. So actually, if we go back, so from our example here, we are finding beta to be here, alpha to be here, and nothing here. Then we look for the relevant inner product. So there is a lot of intertwining operators that map all of those 4 exceptional series function spaces to each other. The question is, where are they taking you from to where? Because we know where our things are. And this one, it turns out that we can immediately use. And luckily, we have an expression. So from that Dobrev reference, we have an expression for this intertwining operator in momentum space. So we will do something like that. This is the tilde version. Now, there's a detail. So these expressions are given in index-free formalism. What you do is you contract the objects with indices via null vectors with certain definitions. If you remove the indices, either you can work with the removed indices or you can try to free the indices. So that's what we want to make sure we are doing right. That's why we haven't put it on the archive yet. But in general, these projection operators involve, these intertwining operators involve a sum over projection operators, which are projecting SOD representations to SOD minus 1. So this is the little group analogy to the Minkowski case. So this is where that appears. And for this particular one with these particular labels, you just need to use this one.
Let's say we get a scalar, make 2 possible expressions of data, but at least for one of them, just the same one. Organizing itself nicely in the data becoming the source and dimension. And then if you want to get a representation of the operator, you have something to that wave function, like you have the which exchanges. So then you have describe information within that wave. That's not the.
No, so these alpha and beta, so these, okay, so these are the 2 things we got, 2 operators at the late time we got. I cannot find the transformation between the 2. So I treat each individually. It gives rise to 2 things. That is, yeah.
Give it some interpretation in terms of correlation. Now, it's not like you can give it interpretation.
I need both of them. That's also how they took. It's like from field and conjugate momenta, 2 things. On this side, you also have 2 things. Immovable.
I can ask that question. Suppose I was very confused with the oscillator
Principle.
I mean, this principle is it right? The phase space, classical phase space, if we broke it up into 2 parts, one which oscillates with one side and one which oscillates with the other, and these 2 different parts phase space each correspond to a different representation.
Yes.
Oscillator, later. Yeah. So the principle is
each are different.
Yeah. Same when it comes.
Yes. Yes. No, I mean they're both principal series.
So in that case, it's for sure what happens is choose rate time.
Okay, but say I just look at solutions the way we put. I have solutions that go with one oscillation, I have solutions to go with the other. Most general solutions that linear on. Like how many oscillations. But now I want to understand representation. So suppose I take the first set of functions. Do they by themselves transform the representation? first set of solutions of it. All bulk waving. I equal plus sign. And in representation theory terms, the power I that one do they constitute one representation? The power minus I yes.
Yeah, that is my understanding.
Yes. Yeah. Okay. So already like a principal series,
You've seen
a
it.
single wave
Already.
equation is a two wave.
Yeah.
Okay. Now similarly for the complementary series, there will be one guy that goes at left time like delta. The other one is like b minus delta.
Yeah.
And again at the representation theory of the students.
Yes.
Now someone is saying the special point looks like 4.
No, still two.
Still.
Alpha and beta. Yes, still two.
Okay. Why do we as it's you associate with an operator? It still maps to one operator. I agree because it's like position and moment. It's like field and particle moment.
Yes.
A function, it can't be a function of both forms and a function. You mean input. Yeah. But I was just thinking just in terms of purely representation. I don't see the ultimate description was the inputs. Something. I'm just trying to understand. Rather than saying you give up.
Yeah, you get both.
There's something very special.
Yes.
Yeah, so exactly. And what is that special thing? The representation that once again splits up. What's the special thing that in other cases these two representations are complex functions? Whereas in this case, these are not complex functions.
Because of these things, how the annihilation and creation operators enter using this plus minus signs. So the complex conjugation will not change that.
Will not change that. And therefore, their complex conjugation is another.
Yeah. Yes.
So we.
Yeah, then it will be these intertwined.
You can still associate one in the typical. Some expressions. Once you say you're in a particular state, right? One of the two parts of that state. The other one is space. I was specifically state. Or the data lies in all one of my regularities. Yeah. So all the data lies in part of you know. But that you need both. It cannot be independently seen. It cannot separately seen. That's why I'm finding it different.
Yes. But yeah, so this was like in the 2-point functions, they both contribute. So alpha is one of them, beta is the other one. In all of them. The polarization test.
Okay, so then. The fact that we see the form, you know, something like the analogy of my mind is sometimes you have a symmetric tensor and symmetric tensor, but actually brings up a self-dual tensor.
Actually, wait, we will do that also.
For SO4.
Yes.
One thing somehow there's the different.
Okay, maybe let's keep going. Okay, so we can identify which inner product to use. Okay, let's go quickly. So this is using the inner product with getting rid of the indices because of the expressions were given. So, okay, somehow we can normalize them. And we worked it out for this case because it was more straightforward. You have to do a bit more detailed analysis for the other one, but you can still do it. Now, we expect this. So we worked with the left-hand side so far. We want to see the split into right-hand side. We want to do something to be able to identify what is the beta plus part of beta, okay? So this was actually Vasilis's clever idea to go back to the field strength tensor and look at self-dual and anti-self-dual split. So now, since we have the solution for the vector field modes, we can just compute the field strength. So all of these we can compute. we can take their late time limit, and this is the transformation. And this is what it means to be self-dual. If you pick up an overall plus I, this is what it means to be anti-self-dual. And it turns out that the field strength tensor breaks into two pieces, so you can write it as the self-dual piece plus the anti-self-dual piece. And we checked that this is preserved, self-duality is preserved under the isometrics. So let's focus on the self-dual part. Let's take its late time limit. Again, it organizes itself into this form. So something with 0 dimension, something with 1. Now we can read off these. And everything will involve alphas and betas from before. So comparing the full expression, we identify the labeled alpha and betas. And this is how we introduce the helicity labels for the late time operators. They come with certain combinations of polarization tensors. Like the same label appears in front of creation, the opposite polarization label appears in front of annihilation. And before doing that, yeah, we could have just given them labels random. And then, well, that's it. So these labels are the labels that go with the discrete plus and discrete minus. And really, this is a summary, so we managed to do this. And these operators themselves also have non-trivial computation dimensions.
So the special thing about B is it even is the existence of it.
Yes.
Second.
Yes. Yeah, but which combination of polarizations? Because this is a specific combination. Which one appears where, right? Yes, yes, yeah.
So the question is what appears in a particular piece. You have to ensure that they don't get mixed, right?
So they track polarization labels, yes, but in a particular way. I'm not sure particularly what happens, but whether it's irreducible or reducible. But even if it is reducible, it will not reduce into discrete series if it's 5 space-time dimensions, for example. So that's it. And if you like, one thing to think on is that this group is interesting for various reasons. It's of interest to cosmology, quantum field theory, and holography. It's at the intersection of Euclidean conformal field theory, De Sitter quantum field theory, and De Sitter holography. It was a bit long, but thank you so much for your questions and comments. So thank you.
Yes.
You.